Hello and welcome to Lecture 13. This is our introduction to quantum physics. In this lecture, we're going to introduce the duality of light to extend our understanding that we picked up last week. After that, we'll have to introduce the principles that lead to quantum theory, which will allow us to investigate the applications of quantum physics. In the previous lecture, we examined the wave-like behavior of light, and physicists have done experiments that have let them observe that behavior. But they've also observed behavior that can only be explained by light acting as a particle. The merging of these two concepts is the domain of quantum physics. So we've seen the wave-like behavior, where light comes in with a wavelength and a frequency and a wave speed of the speed of light. And this behavior can explain concepts like refraction and diffraction and interference. And this allows us to consider energy transfer in very classical terms, which is the way we've seen before about you can continue to add more and more and more energy to an object. And with these experiments, we always see energy transfer with continuous values. So we can send 1 joule or 1 1/10 of a joule or 1 100th of a joule or 1 1,000th of a joule. We can always make smaller and smaller cuts of our energy into different levels. The particle behavior of light is slightly different. So in the particle behavior, we see light move as one small unit. There is a minimum quantity of energy transfer, and we can't transfer any smaller amount of that. So we can either transfer one quantity or two quantities, but we can't transfer 1 1/10 of a quantity. The other way to talk about this is to say that the values are discrete, so they only take on integer or whole numbers. And this is where we get the quantum part, and you want to think quantum connects to minimum quantity. That minimum packet of energy is referred to as a photon. So we're going to shift our focus now to photon energy. A physicist, Max Planck, was able to derive an equation to predict this energy level that a photon carries, and it was able to use that by considering the wave nature and particle nature of light. So remember that we're going to define photon as a packet of energy that's associated with light. I tend to use this circle with a squiggly line in it to represent a photon moving, so we recognize the difference between it and an electron or a proton. And Max Planck's equation is that the energy of a photon will be equal to h times f, where f is the frequency associated with the wave of light. So any photon, even though it behaves like a single particle, is still associated with a wavelength of light. Remember, the wavelength determines the color and energy level of light. And the other piece of information in that equation is h, which is Planck's constant. For our course, it'll be precise enough to look at Planck's constant as 6.63 times 10 raised to the negative 34, and it brings with it units of joules seconds. I know many of you are reading outside of the course, so some other textbooks represent this equation as E is equal to h times this odd symbol that looks like a V, and it's the Greek letter nu. With this consideration of energy, we need to consider a new unit. We're going to consider the electron volt. So an electron volt measures the exact same quantity as joules, and they can be converted back and forth. So a 1 electron volt has been set as 1.602176,634 times 10 to the negative 19 joules. You may recognize this value as it is very closely related to the amount of charge on an electron, because an electron volt is defined as the kinetic energy of 1 coulomb of charge accelerated in 1 volt of potential difference. The reason we make this change in units is because the electron volt will give us values that are in a more appropriate scale as we talk about dealing with energies of subatomic particles. Let's consider an example here. So one of the typical calculations we can see is that we could be asked, what is the energy of the average photon associated with green light? It could be any particular wavelength. We choose green this time. And we'll want to answer this in electron volts for now. So we're going to start with Planck's equation, E is equal to hf, remembering that h is a constant, so that's the 6.63 times 10 to the negative 34 joule seconds. But we're left with the second unknown, and that's frequency. So we consider what else we've been told. We know that the light is green, so that tells us the wavelength of the light. And from last week, remember that light travels at the speed of light. So our wave speed equation can be rearranged to get the frequency, which is the speed of light divided by the wavelength. The speed of light is 2.99792458 times 10 to the positive 8 meters per second. And a typical wavelength for green light is approximately 550 nanometers, and nano is the prefix of 10 to the negative 9. And I'm also predicting that we're going to need to make a conversion between joules and electron volts. Planck's equation is set up to calculate in joules, so we're going to convert it to electron volts as we do our answer. So setting up the equation, substituting for frequency, and substituting our known values along with our unit factor, we see that the approximate energy of a photon associated with green light would be 2.255595129 electron volts. And our limiting factor here is the precision of our wavelength of green light. We picked 550, so we'll treat all three digits as significant and we'll answer at approximately 2.26 electron volts. At this scale, when we're talking about energy, we typically assume that all of this energy is contained as kinetic energy of the photon. I want to assure you that our look at quantum physics is not going into the deep weeds and the newest extents of the field, and we're staying with fairly established quantum concepts. And in an effort to better understand some of this quantum theory, we're going to look at one of the experiments that helped establish quantum mechanics and our understanding of photons. This experiment was the photoelectric effect. In short, if we have light of different wavelengths incident upon a surface, we find that electrons can become energized and they'll behave in several different ways, which could include, depending on the surface, being ejected from the material. Classically, thinking that light is a wave and transfers energy in terms of watts per area, it would be expected that increasing the intensity of the light or allowing the light to shine for longer and longer and longer on the surface would eventually impart enough energy on an electron to eject it from the material. But this isn't what was observed. The quantum theory here observes that the intensity isn't as important to the effect of whether or not an electron is ejected, so much as the actual energy level. So even dim light at the correct wavelength can still eject particles. This ejected electron is referred to as a photoelectron, and physicists really needed to dig into why this phenomenon happened, that electrons weren't ejected at all intensities, and that electrons weren't ejected with more and more kinetic energy as we increased the intensity. So keep in mind, this photoelectron, when it's ejected, it has a mass, we saw that in our previous lectures, and it will have a velocity if it's ejected. So we're looking at the kinetic energy of the ejected photoelectrons. Let's look a little closer at that photoelectric experiment. Say we have some material, and in that material there's definitely some electrons, and we impart on it light of a wavelength of 700 nanometers. So as we saw earlier, that means that it's going to have a specific wavelength, which means that it has a specific color, and it will carry a specific energy of 1.77 electron volts. And no matter what intensity, so what brightness we shine that light on the surface, we see no emission. And no matter how long we leave it shining on that surface, again, we still see no emitted photoelectron. Which is odd. We would think that we are constantly sending energy at the surface. Eventually, we should, in a classical sense, energize an electron enough to jump off the material. But if we send lights of other wavelengths, let's consider 550 nanometers and 400 nanometers, so green and violet, we do see electrons leave this particular material. But when those electrons leave the material, we're not seeing kinetic energies or velocities that we would expect. Again, the classical theory was that if we increase the brightness of the light, green or purple, we should see more kinetic energy on the electrons that come from those lights. But that's not the case that we're seeing. Similarly, in between these wavelengths, we're not seeing particles get ejected in a continuous manner. So the energy here is being very, very quantized. It's got discrete gaps. To understand this, we need to look closer at the structure of the atoms in this surface. Our understanding of the atomic structure is governed by the Bohr model of the atom. Quickly reviewing this model, it's represented with a positively charged nucleus, which is surrounded by negatively charged electrons. Depending on the atom and its specific ion, we'll see a different number of electrons that occupy very specific orbits. These orbits each have their own energy levels that they can occupy. And it's possible for an electron to switch orbits, which means it must transition between different energy levels. For our next couple of slides, we're going to consider the hydrogen atom, and we're going to consider 5 of the levels for the electrons in the hydrogen atom. So in level 1, we have a binding energy of negative 13.6 electron volts. In level 2, it's negative 3.40 electron volts. Level 3 is negative 1.51 electron volts. And level 4 has negative 0.85 electron volts. And level 5 has negative 0.54 electron volts. To move from one level to another, we need to calculate the change in energy of the electron. So this is called an electron transition, and it's another one of our familiar change in calculations. So the change in energy means that we're going to take the energy of its final position and subtract from that the energy of its initial position. Let's look at 2 example transitions. Let's consider an electron that transitions from level 1 to level 3. So its change in energy is energy of level 3, subtract the energy of level 1, which is negative 1.51 electron volts, subtract negative 13.6 electron volts. When we subtract a negative, we end up adding, so we see that we have 12.1 electron volts of energy needed to go from level 1 to level 3. In the other example, let's consider going from level 4 to level 2. So the change in energy from 4 to 2 is equal to the energy it finishes at level 2 with, subtract from that the energy it started with level 4 with, which is negative 3.40 electron volts, subtract a negative 0.85 electron volts. And in this case, we see a negative 3.32 electron volts. So we have to consider what this is trying to tell us. Again, negative signs often lead to confusing situations. If we look at our drawing, as we see the values, they're negative. As we get a bigger negative value, that's a lower energy level. So to move from level 1 up to level 3, our electron must absorb 12.1 electron volts of energy. And to move from the higher energy level down to the lower energy level, then our electron must emit 3.32 electron volts of energy. This is a concept that you're going to need to take a little bit of caution with to ensure that you're considering our energy levels the correct way. Now let's look on a little more closely at what it means to absorb or emit energy. Let's look specifically at what increasing an energy level would involve. This involves photon absorption. Let's take our hydrogen atom and let's shine 4 different wavelengths of light on it. So we're going to impart on this atom a photon with a wavelength of 656.4 nanometers, another one with 486.5 nanometers, a third with 433.8 nanometers, and finally one with 532.5 nanometers, all representing the wavelengths, thus the color of our light. We're going to see if any of these photons would be absorbed by the electrons surrounding our hydrogen nucleus. To do this, we have to consider the possible transitions. While this isn't an exhaustive list, let's look at 3. We could consider an electron going from the first level to the second level, and that would require 10.2 electron volts of energy. And we could look at a transition from the second level to the third level, and we can calculate the requirement there as 1.89 electron volts. And a third possible transition is that an electron could jump from the second level, skipping the third level, and arrive at the fourth, and that would require 2.55 electron volts of energy. So these are several of the possible transitions. Now we have to look at the photon energies that we are carrying to see if any of them would cause those transitions. Remember, this means that we look at the energy of the photon, which uses Planck's equation, except for we're going to substitute for frequency. And we have to remember to convert the joules of energy to electron volts of energy. Let's look at that red photon. So H and C are constants. We've already seen what they are. I'm just going to plug in the wavelength and that unit factor for converting energy. And we see that the red photon carries 1.89 electron volts of energy. So if the red photon coming into our hydrogen atom managed to interact with an electron that was at the second level, then it would energize that electron enough that it would jump up to the third level. Let's consider the green photon, the one with 532.5 nanometers. I'm going to rush through the calculation here, but this photon carries with it 2.33 electron volts. Now, we've already seen from our possible transitions that going from 2 to 4 would require 2.55 electron volts, so we don't have enough energy to make that jump. We have too much energy to go from 2 to 3, and all our other energy requirements from level 1 are much greater than this, and all our transitions from level 3 are much smaller than this. And this is the important part of quantum physics. If a photon comes near an atom and it does not carry exactly the amount of energy that would cause one of the electron transitions, it won't interact with any of those electrons. It will continue and just pass right by. Now, if this happened to encounter a high level electron, then it might be able to eject that electron. But remember, especially for hydrogen, high level electrons are very rare. All of our electrons want to stay down near that ground level. Most electrons will be in the first state. This is that quantized phenomenon that makes quantum physics. Now, what I'm going to leave for you is, will the blue and purple photons be absorbed? And the answer is possibly. We mentioned that an electron at a higher energy level wants to come down to its base. So let's look at what that means as far as energy transitions. So again, using the hydrogen atom as our model, we could consider what happens when an electron transitions from the 5th energy level, jumps all the way down to the 3rd energy level. Here we see that it's a change in energy of negative 0.97 electron volts, which means it's giving up 0.97 electron volts. If we rearrange the wavelength equation, and again, remember that you'd have to do some conversion work here, we get a wavelength of 1,279 nanometers. This is well below the visible range, and it's in the infrared range. Let's consider a different example. Let's see an electron that is on the 2nd level and drops down to the 1st level. Well, we've already done this calculation. That's a change in energy of 10.2 electron volts. And again, doing our calculations, we would get a wavelength of 121.6 nanometers. This is well above the visible spectrum, and this is in the ultraviolet range. Let's look at a transition that's actually going to have an emission in the visible range. Let's go back to the 5th level, and this time let's drop all the way down to the 2nd level. So we do our calculation. We see that we have a change in energy of 2.86 electron volts. We use our rearranged Planck's equation to say that the wavelength is equal to h times c divided by the magnitude of the change in energy. A negative wavelength just wouldn't make sense here. So we input our constants for Planck's constant and speed of light. We divide by our change in energy magnitude, and we divide by our conversion value from our unit factor. And we get an answer of 433.8 times 10 to the negative 9 meters. Remember, 10 to the negative 9 represents the nano prefix. So this is approximately 434 nanometers. So we would get an emission of violet light. If you think back, if we would emit violet light on this transition, going the other way from 2 to 5 means that our previous example, the purple light, would be absorbed by that electron. Okay, with our understanding of energy levels of electrons and how light relates to that, let's go back to our consideration of the photoelectric effect. So we have some material, it has electrons. This time we're only going to shine ultraviolet light on it. So this is not in the visible spectrum and it carries a lot of energy. We have 12.41 electron volts of energy on every single photon in this emission. If we zoom in on this electron, remember it's associated with an atom. That atom has several energy levels that we expect to see this electron possibly at. And if we're able to eject an electron, the amount of kinetic energy it has is dependent on the energy level it was at. The energy levels we saw gave us the magnitude of the binding energy for each atom. So for the levels we have sketched, we would have binding energies of 13.6 electron volts, 3.4 electron volts, and 1.51 electron volts. We can calculate the expected kinetic energy of any photoelectron. Remember, photoelectron is our ejected electron. The maximum possible kinetic energy would be calculated by H multiplied by F subtract phi. Now, phi just represents those binding energies. And remember, H multiplied by F is our photon energy. So given a known substance and a controlled light source, we should be able to calculate the expected kinetic energy of a photoelectron. So what happens if we had light incident on an electron in the first level? So in that case, we are shining our 12.41 electron volt ultraviolet light on the hydrogen. And if the electron available is at the first energy level, we know that it has a 13.6 electron volt binding energy. And when we do that subtraction, we get negative kinetic energy. We see the binding energy is greater than the photon energy. We actually have no emitted electron if the only electron available is at that first energy level. There just simply isn't enough energy to be able to free that electron from its level. Let's look at a slightly higher energy level electron. So what happens if we have an electron at the third level and we shine the same light on it and it interacts? So we have 12.41 electron volts of energy incident on the electron. We subtract from that the 1.51 electron volts of binding energy, and we get a result of 10.9 electron volts surplus. So this is the maximum kinetic energy that an electron ejected from level 3 by a 100 nanometer light source could have. It doesn't matter how intense our light source is. Depending on the wavelength, that's what determines the amount of energy we're imparting. And this is the part of the photoelectric effect that classical physics couldn't explain. We only get those ejections based on the color or wavelength of light, not the intensity of the light. Well, that explanation was useful for us to understand what's going on with a photoelectron and the photoelectric effect. It's not typically the way in which we employ our understanding of this concept. The way we actually use this is that we will have a controlled applied ultraviolet light, and we choose ultraviolet because of how much extra energy it brings with it. And we'll have a detector that will measure for kinetic energy of a photoelectron, which means if we rearrange our previous equation as phi is equal to HF minus kinetic energy, we've detected the kinetic energy. We're subtracting that from the controlled applied ultraviolet light. And this allows us to calculate the binding energy of an unknown substance. So we're able to use an electron spectroscopy tool to identify unknown substance by comparing the kinetic energy of its photoelectrons to known sources. Each substance has its own binding energies, which means it'll have its own spectral pattern of emitted photoelectron kinetic energies. And we use that detected pattern to compare against known samples. This lecture, we began our look at quantum physics. So we examined the quantized nature of the interactions between electromagnetic radiation and matter, so light sources and atoms of substances. To do this, we reviewed the Bohr version of the atomic model and the energy levels associated with electron orbits that are possible for each atom. We looked at calculating the relationship between photon wavelength and the electron energy levels, and we considered the application of these concepts in quantum mechanics to spectroscopy. Next week, we'll go on to look at some of the more nuanced pieces of quantum physics.